Hi, I am Sanjay Patel. We have seen our previous video that how to transform a given double or triple integral into new coding systems. That is, how to change the variables or parameters in the given double or triple integral by means of Jacobian. So, change of variables is very important sometimes when the given double or triple integral is very complex. Then we change the variables to some new system and the problem becomes more easy. For example, if you have a double integral over a region R, where R is some region in the Cartesian plane with variables x and y, then we can take some substitution x and y in terms of some other variables, say x as a function of u and v and y also as a function of u and v. Okay, then this double integral we can transform into a new double integral over a new region R dash, where x and y are replaced by these relations, and you will get a new function in variables u and v, and this dx into dy is changed with the value mod of j into du into dv, where j is the Jacobian of xy with respect to u comma v. So we have seen this transformation formula for double integrals and also for the triple integrals. So you can refer or you can watch that video and check that how we have obtained various transformation formulas. So in this and the coming 2 or 3 videos, we are going to solve problems of change of variables in multiple integrals, or change of you can say transformation of multiple integrals from one system to another system. So in this first lecture in this series, I am going to solve first problems on changing the multiple integrals into an arbitrary system of coordinates. So let us understand this by various examples. Let me start with the first one. Say, find the value of the double integral e raised to y minus x upon y plus x dx into dy over a region R where capital R is a triangle, is the triangle bounded by the line, the straight line x plus y is equal to 2 and the coordinate axis, You know that this function under this double integral sign is a little bit complex to integrate with respect to x or y first. So what we can do here is we can change these variables x and y to a new system. This you'll understand by solving various problems. So let me start with this first one. Here this x plus y appears at these two places, in this as well as here. So let me take some substitution for say x plus y and something for this y minus x. So let us take say y minus x is equal to u, and let me put y plus x is equal to v. So let me take these substitutions and see what happens. So whatever some similar part or say some complex part you see in our integrals or in our given conditions, you can think of taking substitution for such expressions. As I have done here, I have taken y minus x is equal to u and y plus x is equal to v. Okay. What I want to do is I want to express first this x and y in terms of u and v. So how can we solve this? It is very simple. Suppose if you add these two, what you will get is 2y is equal to u plus v. So we will get y is equal to 1 by 2 times u plus v. Correct? Also, if I subtract this equation minus this equation, that is, if I take u minus v, now what I will get is y will be cancelled, and I will get say x, rather 2x y minus x. Okay, so I am subtracting this way, and let me do this way, v minus u, taking v minus u, what I will get is x minus x. So I will get plus 2x is equal to v minus u. So x is equal to 1 by 2 times v minus u. Is that right? If you don't understand, you can write all the steps. So in short, what I have done is I have solved these equations for x and y and made x and y subject to the formula. The reason is here x is expressed as a function of say u and v, which is 1 by 2 times v minus u. Okay, and y is also expressed as a function of u and v. It is equal to 1 by 2 times u plus v. The next step is we'll compute the Jacobian for this x and y. So now the Jacobian j of x and y with respect to u and v is given by, the next step is always find the Jacobian delta x by delta u, delta x by delta v, delta y by delta u, and delta y by delta v. So this way you find the Jacobian. We have to differentiate x and y with respect to u and v. And let us see what we get here. So this x is a function of u and v. If I differentiate partially with respect to u, v is constant. So derivative of v is 0 and derivative of u is 1. So we'll get 0 minus 1. So it is only 1 by 2, that is minus 1 by 2. Correct? It is very simple. And differentiating x with respect to v now, u is constant. So derivative of u is 0, and derivative of v is 1. So we'll get 1 into 1 by 2. So it is 1 by 2. Then we differentiate y with respect to u and v. You will get 1 by 2 and 1 by 2. It is very simple. Derivative of y with respect to u is 1 by 2 into 1 plus 0, and derivative of y with respect to v is 1 by 2 into 0 plus 1. So you will get this thing. Simplifying, what you will get is minus 1 by 4 into minus 1 by 4. So this into this minus this into this. So we'll get, finally, it is minus 1 by 2. So value of the Jacobian in this case, we are getting as j is equal to minus 1 by 2. Okay, let us keep it in the box. Fine. Now let us concentrate on the given region of integration. This integral we want to evaluate over the triangle. This region R is a triangle in the xy plane, which is bounded by this line x plus y is equal to 2 and the two coordinate axes, that is x-axis and y-axis. So it is very easy to draw the figure. So let me first take say x-axis, y-axis, and then draw this figure. So first of all, the region R is bounded by x plus y is equal to 2 and the two coordinate axes. So the equation of y-axis is x equal to 0 and equation of x-axis is y equal to 0. So it is bounded by these three lines. Now let me draw the coordinate axis. Okay. Another axis. So this is x-axis, this is y-axis, and this is origin. And let us take the line x plus y is equal to, say, 2. It makes some intercept with x and y axis. So it will be like this. You can take this way. Let me change the color. Okay. So this is the line x plus y is equal to 2. So it is intersecting the x and y axis at these 2 points. It is clear. We know the general equation of a line making intercept a and b with x and y axis is this. So this point is, say, 2 comma 0, and this point is 0 comma 2, and this is our y-axis whose equation is x equal to 0. This is x-axis whose equation is y equal to 0, and the triangle is this triangle. This is our region of integration. But we know that the given formula, the given function which is to be integrated is complicated. So we want to change this integrals. So in the new given system, UV system, where we have taken the substitution, in the new system, or coordinate system, that is UV coordinate system, we have the following new bounds. So we have x equal to 0, y equal to 0, and x plus y is equal to 2 are the three, say, sides of this triangle. So x equal to 0, that corresponds to, you know what is x in terms of u and v. Let me show you. X is 1 by 2 times v minus u, and y is 1 by 2 times u plus v. So x equal to 0, that gives us 1 by 2 times v minus u equal to 0, and that is v minus u equal to 0, or you can say v is equal to u. So this is my first side of the triangle in the new system. Then y equal to 0 gives us 1 by 2 times v plus u equal to 0, and that gives me v plus u equal to 0, and therefore v is equal to minus u. So this is our second side. And the third side, that is x plus y is equal to 2, we can write as x plus y is equal to 2. What is x plus y we have taken? We have taken x plus y is equal to, I think, u or v. Yes, it is v. X plus y is equal to v. So I can replace this third side of the triangle by v is equal to 2. So these are the three, say, boundaries or sides of the new region of integration. Okay. Remember, x equal to 0 is this, which is transformed into the line v equal to u. The line y equal to 0, that is x-axis, is transformed into the line v equal to minus u, and this line x plus y is equal to is transformed into v equal to 2 because of our substitution. Now I will draw the new region of integration in the coordinate system where variables are taken as u and v. So instead of x and y axis, here I will be having, say, u and v axis. So let me take this way. This is my v axis. Then this is u axis. Let us call this as u and this is as v axis. U axis and this is v axis. Okay, and this is my new origin. Okay. Now in this new system, I want to take these three curves. V equal to u. It is similar to y equal to x. What is the graph of y equal to x? Straight line passing through origin. Okay, and making 45-degree angle with the positive x-axis. But instead of x-axis, we have u-axis. So I must draw a straight line which is passing through the origin and making an angle, say, making an angle with this. So this is a straight line given by, say, v is equal to u. Okay, and second line I am taking as v equal to minus u. Okay, so this is my line v is equal to minus u. And the third line, that is v is equal to 2. We have plotted the graph for this and this, and now v equal to, v means you can compare with the y-axis. This is something like y-axis, and y equal to constant means line parallel to x-axis. So v equal to 2, that is v is equal to constant, means we will have a line parallel to the u-axis. So our third boundary is a line parallel to this u-axis, and that is given by v is equal to 2. Okay, it is like this. Fine. So the region, new region of integration is this area. It is again a triangle, but this area bounded by these three curves. Okay. So now we want to integrate over this new region, which I am calling as, say, r dash. This is I am calling as r dash. Okay. So we have our transformation formulae. Let me write that. We know that double integral of a function of two variables over region R, when it is changed into the new system u and v, where x and y are functions of u and v, as I have discussed earlier, we have this formula. Everywhere when x or y appears, we substitute the relations and get a new function of u and v, and here we write mod j into du, sorry, this must be du into dv. So according to this formula, we can write double integral, the given double integral e raised to y minus x upon y plus x dx dy over the given region, over the original triangle, that is equal to double integral over the new triangle r dash in the uv system. We have taken y minus x is equal to u and y plus x is equal to v. So this becomes e raised to v upon u. U upon v. we have taken y minus x is equal to u. So this is u and denominator is v. And dx dy is replaced by mod of j. What was j? The value of the Jacobian. The Jacobian was minus 1 by 2. This we have calculated. And let me also show you the that x and y, or yes, y minus x is u and y plus x is v, and Jacobian j is minus 1 by 2. So putting the value of Jacobian in this modulus, so mod of minus 1 by 2 into du dv, So always we are writing the absolute value of this Jacobian. So in short, we have to integrate this 1 by 2 over the new region R dash for this simpler function u upon v. Let me write it properly. This is equal to e raised to u upon v du dv. So instead of this complicated function, now our problem becomes very easy. Now in the region R dash, in the region R dash, let us decide that with respect to which variable we should integrate first. You see, if you want to integrate with respect to the variable v first, you must take an arbitrary strip parallel to v axis. V axis means y axis. So if I take a strip over here, then my end curves, the end parts of the strip, here it is lying on this line and here it is lying on this line. But if I take a strip over here, then it is lying on this line v equal to minus u, and here it is lying on the line v equal to 2. That is, for different positions of these vertical strips in the region of integration, the end curves are changing. So that is not a nice region. In this case, one should divide the region. But instead of that, means instead of integrating with respect to say v first, let us try to integrate with respect to u first. So u means x. You can compare with x axis. So take a strip parallel to u axis in the region of integration, and you check all the position of this strip. For all the position of the strip, the left hand curve and the right hand curve remains same. Here the left hand curve for any position of this strip, yellow strip, is this line v equal to minus u, and the right hand curve for all the strips in this region which are horizontal is v equal to u. So this is a regular region if you integrate this way. So after taking an arbitrary strip, what we decide is the curves, these equations of the curves. Okay, we are integrating with respect to say this u first. So u will be a function of v. So I can write the equation of this as u is equal to minus v, because we are given that it is v is equal to minus u. So the same equation I can write as u is equal to minus v. And this v is equal to u or u is equal to v, both are same. Let me write here. This is v is equal to minus v, that is phi of v, and this is u is equal to v, so it is psi of v. So this kind of boundaries are there. And to determine the limits of v which are constants, we have to go in this direction. And when you enter in this region, the first point we are getting here is the origin whose coordinates are 0, 0. So minimum value when you enter in the region is this 0. And when you come out of this region, when you exit the region, the maximum value of v is on this line. So we have to come out of this region through this line v equal to 2, that is this pink line. So at any point on this pink line, the value of v is 2. So our v varies from v equal to 0 to v is equal to 2. So keeping in mind all this, now I can write the limits of integration here. What I want to do is, this is equal to 1 by 2 times. So I am integrating with respect to u first. So limits of u will be functions of v, and then with respect to v. The limits of v will be constants. We already obtained the limits of u. Let me show you again. U equal to minus v to u is equal to v. So I will write it here. U equal to minus v to u is equal to v. Okay. And limits of v, which are constants, which we have determined by walking through the region. The minimum value of v is 0 and the maximum value of v when you come out of this region is 2. So v varies from 0 to 2 in this region. We have 0 less than or equal to v less than or equal to 2. And that u varies from 5v to psi v. Means u varies from minus v to plus v. So I can write here v is equal to 0 to 2. And the function which is to be integrated is e raised to u upon v du into dv. Sorry, this is first with respect to u, so it is dv du, dv into du. So let us find the value of this integral. This is equal to say 1 by 2 times integral v equal to 0 to 2 into this. Oh, I forgot to write u equal to minus v to u is equal to plus v. This is u is equal to minus v to u is equal to plus v. We have seen the limits of u. Let me show you again. U varies from minus v to u is equal to plus v. So I should write here u is equal to minus v to u is equal to plus v, and v varies from 0 to v equal to 2. You can write like this also. So this now I have to integrate this function with respect to, let me write one more step. This is equal to u is equal to minus v to u is equal to plus v e raised to u upon v du and then dv. So we are integrating with respect to u first. Just I have written one more step. Now this is equal to 1 by 2 v equal to 0 to 2, and now I will write the value of this integral. When we are integrating with respect to u, v is constant. So this is something like e raised to ax. What is the integral of e raised to ax? You know, this is equal to 1 upon a times e raised to ax. So just you have to take the reciprocal of the coefficient of x when you integrate. Here we are integrating with respect to u, and the coefficient of u is 1 upon v. Its reciprocal will be v. So it is v into integral of e raised to x is e raised to x. So this is as it is. And then this we have to substitute the values. U is equal to minus v to plus v, and then whatever answer we get, that is to be integrated with respect to v. So let us find the value of this. 1 by 2 times v equal to 0 to 2, putting value of u equal to v first. Remember, these are the limits of u. Let me write this way. This is u is equal to minus v to u is equal to plus v. Just to make it more clear, I am writing u equal to v here. So wherever u is there, you have to put v. So this v remains as it is. Putting u is equal to v, we get e raised to 1. And then putting the lower limit of integration in place of u, v remains as it is, constant. Putting the value of u equal to minus v, we get e raised to minus 1 into dv, which I can write as this v is a common factor. So what is left is 1 by 2 times v equal to 0 to 2 into v into e minus e raised to minus 1 dv. So I can take the constant e minus e raised to minus 1 outside of this integral sign and rewrite this as 1 by 2 e minus e raised to minus 1 integral v equal to 0 to 2 v dv. So that is equal to 1 by 2 times e minus e raised to minus 1 into, now integration of v is, it is v square by 2, and then put the values of limits of integration v equal to 0 to 2. So putting v equal to 2, we get 4 by 2. Let me write the step. So what we get is 4 by 2 minus 0 by 2. Okay. So it is nothing but 2 only. So my final answer, everything will be cancelled here. This is 2 to the 4 and this 2 will be cancelled with this 2. So our final answer is e minus e raised to minus 1. So the required double integral, which is given over the triangle of e raised to y minus x upon y plus x dx dy over the region R is e minus e raised to minus 1. Okay. So we'll solve some more problems of this type in the next lectures. And now we'll not discuss everything in detail. Just you remember or revise all the transformation formulae for changing the variables in the multiple integrals, what we have seen in our last lecture. So in this lecture, I have shown you how to transform a given double integral from the Cartesian system to an arbitrary system UV. Okay, and you have seen that the problem of evaluating this double integral becomes so simple if we change the variables. So thank you.